Okay, off we go. So here's where we were last time. We were almost done with chapter 3, not quite, almost. We were talking about this little diagram, this little composition of operators that kind of comes out of nowhere. I mean, the obvious observation you can make is the Legos don't fit together, right? I mean, you can take what comes out of the gradient operator, and that is, in fact, exactly what goes into the curl operator, right? So, I mean, this is something one could do. Why on earth would one want to do this, right? And so I've made the observation last time that this is what we call an exact sequence, asterisk. There are some little subtle issues that we're not going to need to worry about in this class, and for the level of rigor that we're going to be going into, this is a close enough kind of a statement. Punchline, other than some exceptions and regularity concerns, everything's got a lifetime of 2. And so I talked last time about what I mean by this, and again, this is just a metaphor, right? I probably got this from somewhere else decades ago and don't remember, but as far as I'm aware, I made this up. And the idea is that every participant in this diagram has a birth and a survival and a death. Death being 0, it's nothingness that remains nothingness. Anyway, that's my metaphor. It's a little dark, but whatever. For example, if you have a vector field and you take the curl, fine, go ahead. But if you compute the divergence of that curl, of that original vector field, you will get 0. And kind of likewise the other way around. Let's suppose that you have some non-zero vector field and you compute the curl, and let's suppose you get 0. Let's just say. What would we conclude if this were to happen? And the claim that I'm making is that, again, everything has a lifetime of 2. So if this is where the death happens, then this must have been survival, not birth. It must have been born here to have a lifetime of 2. Right? It's this oddly rigid, almost always, for all practical purposes, pattern. And that means there must be some function whose gradient is that original vector field. All right, so this is going to turn out to be really useful, but this isn't really quite my motivation for bringing this up. My motivation for bringing this up is to persuade you that we are sailing over deep water right now. There are powerful ideas afoot. This is not just a simple matter of, curl computes rotation of the fluid and divergence computes, outward flow. It's not as simple as that. There's a lot going on, and the patterns that we're going to notice and the geometric connections that we're going to find when we get into chapter 6 and 7 are bonkers powerful. And I just kind of wanted to just give you a little bit of a glimpse of these kinds of things, and so you'd be open-minded to learn a lot in chapters 6 and 7. Lots to say in chapters 6 and 7. Okay. All right, and that will do it for chapter 3. Now, real quick, let me go back over to the reordered, reordered for my sections content syllabus. And so we finished chapter 2, and then we went on to chapter 3, minus the, of course, section 3.1 that we did a little early. And then, wait a minute, how come it goes to chapter 5? What happened to chapter 4? Right? And the answer is we're going to cover chapter 4 at the very end of the course. Sort of out of order, and I just want to give you a quick comment as to why that is, and it's roughly the point here is that putting it where it was unnecessary. It's not prerequisite to anything else that we're going to be doing later in the course. And chapter 6 and 7 takes a lot of time to kind of digest and process and kind of mull around in your head. You need time to get accustomed to that. And as early as we can do chapter 6 and 7, the better. Right? So I'm basically racing to get to chapter 6 and 7 as fast as we can. And then anything that is not essential to that, that's an overstatement. Anything that's not needed, let's say, toward that goal, can come later. Right? We'll do that stuff when we have a chance. So chapter 4 is going to be covered at the very end. You'll see that on the thing here. Right after chapter 7, we are going to then come back and do chapter 4. So anyway, I just wanted to point that out, make sure nobody got confused. So we are skipping chapter 4 only temporarily, but we are temporarily skipping. Okay, so let's talk about integrals. We've been doing derivatives. Right? And first, a big picture observation. When we started talking about derivatives, the very first thing we did is I said, we're going to try to take old single variable calculus ideas, we're going to try to generalize them to a multivariable setting and try to come up with something kind of analogous. So what should that mean? Right? We had to kind of ask ourselves the question, what is fundamentally, what do derivatives do? What is the purpose of derivatives? So we know even what we're trying to make something analogous to. We're trying to generalize what, right? So same question with integrals. And I'm going to take a moment. I'm going to take a few pages here, actually, to kind of segue into answering that question. Like, what is it, in fact, that we're generalizing? So anyway, I'm going to start with the wrong answer. Just like we did in chapter 2, we started off talking about partial derivatives, and I'll remind you, our partial derivatives fundamentally deep down, is that what multivariable derivative, is that really how you should think about multivariable derivatives? No. It was a foot in the door, it was convenient, it was an obvious first step, but in retrospect, it was just not really quite right. I mean, it's a useful tool, blah, 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 but we have better points of view on derivatives now. So that's what we're going to do now. We're going to come up with a reasonably natural first step that we're eventually going to kind of look back on and be, not exactly embarrassed about, but we're going to realize all the shortcomings of what was about to happen. Okay, so flashbacks, single variable calculus. You have an area, and if you rotate that area around the x-axis, that makes this volume. And if you want to compute the total volume of that, whatever that thing is, sideways base, maybe, how would you do that? And y'all remember, I assume and hope, keyword assume, that what you do is you take that and you break it up into a bunch of little slices of volume. And then you ask one at a time, what's the volume of these slices? Now, the volume of the slices is going to be cross-sectional area times a thickness. That thickness is dx. So anyway, like I say, old news. This was an old strategy that the whole is the sum of the parts. You can take a solid and slice it up into much easier to understand little smaller solids. And because they are smaller and easier to understand, those you can write formulas of. Okay. All right. So that noted. Here's the, I don't know, for lack of a better idea, seemingly a reasonably similar, maybe kind of analogous question. Suppose that I have a surface, that being specifically the graph of some function of two variables. And just to get the ball rolling, we're going to assume f is continuous and non-negative. We don't want to deal with little distraction, not the point issues for the moment. Okay, so suppose I want to compute now this volume, the volume under that surface but over the xy plane, but specifically over a certain rectangular base. In the xy plane. All right, does everybody see the question? And how would you do this? And just kind of copycatting from what worked in single variable calculus, what we were just talking about a second ago. You take the whole and you slice it and hope that those slices are easy to understand. Okay, so here we go. Slicing this up into little pieces. I again, seems like a reasonable first thing to try. I get a bunch of, my little silly metaphor for this is that this is a loaf of bread, and this is a slice of that loaf. So, how would I compute the volume of this slice? Okay, well, that's an easier question, and I can try to say, well, it's got a certain amount of a thickness there. I'd naturally call that dy, because that's a little thickness in the y direction. Seems like it's totally analogous to what we did over here, except here that direction happened to be called x, and so that's why this was dx. So what's with the area, though? Right? How am I going to get my hands on this cross-sectional area? And is that a disc? No. Is it a square? No. Is it a rectangle? No. Is it a triangle, or is it any other sort of barnyard variety geometric figure that I can just write down the formula for the area of? No. So this is where in a single variable calculus class they will throw up their hands and say, well, we can't do this. We just bumped into a brick wall and nothing we could do. Okay. All right, here's what we're going to do instead. We're going to notice something, a couple of critical observations about this area. And keep in mind, here's that area that we want to compute. That area is the area under a curve. Right off the bat, I'm psyched because area under a curve, oh my gosh, area under a curve. I remember that phrase. I know how to compute area under a curve. Sweet. We can, and okay, wait a second, slow down. We know how to compute the area under the graph of a function. Specifically, I need to have a formula for height so I can talk about, for any little piece of area, I need to be able to talk about height times the width of the base. So can I, on this little piece of area, or said differently, under this curve, can I talk about height? And the answer, yeah, absolutely. Because this curve came from some surface. That surface was literally given to us as the graph of f. That means, very specifically then, that the height here, I think the light blue shows up better, that height being z, the curve having come from a graph with this equation, that is f of x comma y. So I have explicitly a formula for height, and I can talk about height times the sort of the width of the base here, and that'll give me the area, and I can just straight up add this up with an integral. And that all together, let me color choices. Why don't I do this with the highlighter? This area is an integral, and again, just to keep the color coding going, that's height f of x y, as we just discussed, and then times width. Now keep in mind that width is in the x direction, and so that is dx. Now there is something creepy about this integral. I want to fully recognize the creepy on this. We've seen dx integrals before. We've computed areas with dx integrals before. That's all perfectly normal, but we have not seen a multivariable integrand before. So this should give you concern. You should be thinking that's weird. You should be uncomfortable about the fact that this is a multivariable integrand, right? Everybody on board? Okay. Let me try to put your mind at ease about that. I claim that's an illusion. This is not a multivariable integrand. And is a single variable integrand. Because you got to keep in mind, what specifically are we doing? And that is, just to clean up the mess, let me get rid of all the, there we go. We are moving in that direction. We're moving in the x direction, right? X starts at A and then x ends at B. Yeah, sure, but notice y is constant. As I compute this cross-sectional area, as I compute this, again, purple integral there, I didn't change a bit. constant. That's the whole point of this integral. The whole point to this integral is that I want to know for a given and therefore fixed value of y. I want to know a cross-sectional area. For that given y. Y is fixed before we even decide to write down the integral. Is that cool? Everybody happy with that? So as far as the computation of that integral is concerned, y is a constant. That means y being a constant, that's a constant. And then as promised, this integrand has only one variable. That variable is x. And then also in the integrand, there's a constant that is named after one of the later letters of the alphabet, but it's not a variable. Okay. All right. So it's all over but the shouting then. We win. Let me just kind of put the pieces together. Let's see, as we have argued previously, let's see, I've forgotten what colors I used, but we knew we were going to be doing an integral dy, right? We had that decided back here. We were going to, as y goes from c to d, we were going to look at all these cross sections. Okay, so you see here, y going from c to d, and then just like in this previous example back here, we know our integrand is going to be our cross-sectional area. Great. We just computed the cross-sectional area. The cross-sectional area is that integral. That being, you'll notice, a dx integral because x is going from a to b. And then all together, lo and behold, like I say, we're done. We win. The grand total volume that we wanted to compute is this very scary looking expression right here. It's called an iterated integral. But it's an integral of an integral. And that is, again, we're back to being worried about that. Can you do that? Is that legal? Does that even make sense? And yeah, it's perfectly legal. It's no problem. Because ultimately, you look at these integrals one at a time, and let's start with the inside. This inside integral, don't worry about where it came from, right? This inside integral, we're just looking to compute this area where y is a constant for the purposes of that entire question even. And so notice just for the pattern of it all, the outside variable is constant for the inside integral. So, single variable integral, nothing to it. Perfectly legal, no problem. And now what can I say about the outside integral? Well, the outside integral, that outside integral has an integrand, and that integrand is, you'll notice, a function of a single variable. That is an integral of a of y dy, again, single variable calculus, no problem. Okay, let's pause for a second. How are we doing? Everybody following the strategy there? Okay. Yeah.
I assume for this, order doesn't matter, and we will.
Whoa, hey, no, yeah, order absolutely matters. Okay. Yeah. No, I've made a very specific calculation here. I've relied critically on the picture to justify the steps. Now, you're getting at, there is a later point that we're going to observe in a couple of pages. You can do this the other way, and there are strong connections, and there's a pattern sometimes.
Okay.
But it is not something that you can rely on. Yeah. Is that satisfying? Okay. All right. Okay. All right. Let's see here. Okay, so we're going to do an example momentarily. I do want to point out the awkwardness of language. There's a temptation to refer to these as, because on the one hand we have that integral, and on the other hand we have that integral, and there's a temptation to call them the first integral and the second integral. The problem is when we wrote down this expression, when we started to motivate why we would be interested in this integral in the first place, the very first of these integrals that we wrote down was the blue integral. And then we subsequently figured out what that inside needed to be. Okay, when it comes time to do the computation, we have to evaluate the green integral first. I can't evaluate the blue integral first. I don't even know what its integrand is yet. Right? So you really have to integrate starting from the inside, even though you develop and motivate starting from the outside. So with that in mind, I mean, we have to look at this terminology, you know, the first integral and the second integral, and recognize that that's pretty vague. First in which sense? Right? And this is a problem. It can lead to definite confusion and ambiguities. So I suggest that we don't even use that terminology. I strongly encourage y'all not to refer to these as first and second. There's a perfectly natural way to refer to these, and that is to refer to them as the inside integral and the outside integral. And someone who understands what's going on here will then have no ambiguity in their mind of which integral you're talking about and what part that plays in the computation. Okay, so careful about that terminology. Alrighty, let's do an example. We're going to compute the volume under this graph. Right? Keep in mind, graph means z equals and all of that, so that gives us a surface, graph of a function of two variables. We want to compute the volume under that graph, sitting over a certain rectangle, and that's this rectangle down here. And let me just point out first, before I'll come back and talk about that notation in a second, but this is exactly the question that we just already answered. You want to compute the volume under a graph of a function of two variables, continuous, non-negative, right? This totally fits the form of what we just talked about. So I can immediately just say, oh, yeah. So I guess that volume is this iterated integral right here, just copying from what we've already argued. Okay, let's talk about this notation a little bit. This is a little bit of a weird notation. Referring to this orange rectangle here with 0, 1 kind of times 1, 2. This looks like, I mean, is that a multiplication? No, because these are intervals. Is this a cross product? No, because these aren't vectors. So this is just an awkward reality that there's just not enough symbols on a typewriter that we can use in math without having to use some a few times, right? And so this times right here doesn't mean times, it doesn't mean cross product, it's just a different usage. And specifically, here's what it means. Whatever interval is listed first is telling you the range of values of the first variable, in this case x. The interval that is written second is telling you the range of values for the second variable, in this case y. And now I think I can persuade you that if you look at this range of values of x and that range of values of y, then between the two of them that defines literally this rectangle, and so that's what that notation means. Everybody okay with that? All right. Okay, so off we go. A couple of single variable integrals here. I'm going to say, roughly speaking, there's nothing to be afraid of on this. It's not quite true. There are a couple of landmines. These are just observations of how not to misinterpret what we're doing. Ultimately, big picture, we're going to compute a single variable integral, and then when we're done with that, we're going to compute another single variable integral. Right? But here's the landmines. Here's what you can inadvertently mess up. So let's look at the very start here. How do I do an integral of x squared? It's 1/3 x cubed. Nobody's surprised by that, I hope. It seems like exactly what we ought to do. And then here's the first landmine. A lot of people will look at y squared and think, 1/3 y cubed? Right? Sounds familiar and all, but nope. It's x times y squared. And the very important reason why is you got to keep in mind For the purposes of the let me scroll up to where I have this written down, in fact. For the purposes of the inside integral, the outside variable is constant. And that's your job to remember what roles, which variables are playing at which stage of the calculation, right? So we're looking at this inside integral. The outside variable is y. So as we compute the inside integral, there we go, y is constant. And that means y squared is constant. And what is the integral with respect to x of a constant? Well, constant times x. Everybody happy? Heads up, right? That's a landmine. That's definitely something you can inadvertently forget. And then, of course, then you get dramatically wrong answers. Okay, here's the second. I'm going to call it a landmine. It's just an easy mistake to make, but once you've done the antiderivative, we take the bounds and we copy them down, and a lot of people like to write down just those bounds. That's what they taught us in high school, or Calc 1 anyway, whatever. And then you take those values and you start plugging them in, right? So we might, for example, take this 1 and just kind of start plugging it in for stuff. And already made a mistake. Very importantly, when you're doing that inside integral, which we're still working on, right, it remains y is a constant. You don't plug in these values for y, you plug in these values for the variable. There's only one variable at this point. That variable is x. These values get plugged in for x only. And look what I did here. Silly me, right? I'm sitting here plugging those numbers in for y. You don't. It doesn't make any sense. Y is a constant. It's, I don't know, some number between 1 and 2. It's going to eventually be all the numbers between 1 and 2, but for the moment it is some number between 1 and 2, and it is definitely not ever 0. Everybody on board? So easy mistake to make. Now, my personal hack to help me avoid making this mistake is to just put a little reminder here. X equals 1, x equals 0, in recognition that x, and that didn't go right, that x is the variable in question. And now look, you don't have to do this. You're not mathematically wrong if you don't write x equals 0, x equals 1. But this, I think, is a mistake avoider. So for strategic reasons, I urge that you do this. If you don't write x equals 0, x equals 1, you're just all the more likely to kind of forget what you're doing as you plug stuff in and accidentally plug in something nonsensical. Everybody good? Okay, and then we plug in those values and do a little algebra simplify. Not much, I guess. And what we have there is we have computed this inside integral. That inside integral is that. Now wait a second. It doesn't look like we've computed it. What about the y? Well, keep in mind, for the purposes of this inside integral, that y is a constant. So in fact, we have computed, to the extent that the inside integral possibly can, we have computed that integral. And keep in mind why we have that inside integral. We have that inside integral because that is a of y. That is my cross-sectional area in the y direction. It's supposed to be a function of y. Okay, now, having noted that, let's now kind of move on and think about the outside integral. The outside integral, after all, y goes from 1 to 2. Now what do I do with y? Well, for the purposes of the outside integral, y is explicitly the variable. Now that the inside integral is all done, I reinterpret y now as the variable for this integral. This is no longer a constant. I'm now letting this vary over all the values between 1 and 2, as indicated there. right? And so I do another single variable integral. Now this time, variables are playing different roles, so you get a different thing. Remember, up here, we went to some trouble to observe that y squared's antiderivative was xy squared. But now that this is actually a variable, its antiderivative, 1/3 y cubed, because y is the variable. How we doing? All right. And then a little arithmetic, bada bing, bada boom, you got it. I'll let y'all do the arithmetic. By the way, make sure all the single variable calculus, just a reminder, that's in the prerequisite trail for this course. And so, yes, I have to assume that y'all are all good with all that. If you might be a little shaky, perhaps, right? A lot of students are. Historically, we see this in this course. It's been a while since y'all have done Calc 2. Didn't come up to speak of in linear algebra, probably. Be a good time to polish up those old skills. Make sure you're good with, the basics, right? Standard functions, power rule, substitutions, integration by parts. If you want to kind of ignore inverse hyperbolic cosecant, yeah, totally, right. I have no plans to use any integrals of inverse hyperbolic cosecant, right? But the basics, you need to make sure you're strong. Okay. All right, now, to your question. Can you do this in the other order? I'm going to mostly leave this as an exercise for y'all to think through on your own. It's very analogous to the arguments that we just made. It is not the same, right? The picture is geometrically different because we're going to be going in a different direction. We're kind of slicing initially in the other order. So everything has to be reconsidered, rethought through. And I'll tell you what the answer is. Yep, totally, it's fine. And here's what you get. Computing the volume by slicing up the bread in the other order. Get something very similar looking. So that then, now we have this new formula for the volume. We already developed this old formula for the volume. And so you might say it follows that this integral and this integral are the same. And then you notice that the inside variable and bounds become the outside variable and bounds, and the outside variable and bounds become the inside variable and bounds. It's like you're doing this right here, right? You're just switching. By the way, very important that you switch them together, right? You got to switch them together because the x bounds are the x bounds. Slicing in the other order does not automatically somehow change your domain to the x values or the old y values or something like that, right? So very important that they switch together. But yes, you can do that with the very stern warning that this works only when the domain is a rectangle. Now, that's the only thing that we've even considered at this point. Sure, right, fine. So yes, this does work. For rectangles, very soon we will get around to talking about integrals where the domain is not a rectangle, and in those cases, this does not work. So don't get too comfortable with this idea that you can just kind of switch the bounds and switch the differentials and it's all good. Rectangles. Okay. All right. We've got a pretty cool answer here to a pretty natural question. How do we compute the volume under a graph? And let me just remind you, in your experience learning calculus, once we knew how to compute the area under a graph curve, in other words, the single variable version of this, you might say, oh, well, my gosh, we were able to answer just tons of other questions. And we were writing down how much work does it take to blah, 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 and how much mass is there in the blah, 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 and what's the population of the blah, 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 right? And we just tons and tons of applications, just boom, seemingly automatic, and just all the dominoes fall. So it's tempting to say that we have basically gotten to that point in the multivariable context as well, and I'm sorry to report that no, we have not. We have solved one geometry problem, and that's it. So let me try to persuade you why this just doesn't answer related questions, such as, for example, if you wanted to compute the mass of a rod of non-constant density, right? That would be the single variable sort of first next example. Now we're going to say, well, let's suppose we want to compute the mass of a rectangular sheet of non-constant density. Right? Two-dimensional instead of one-dimensional. And y'all remember, this is a single variable, if we were looking at the single variable mass of a rod, well, you just do an integral of the density, and stuff just kind of works out. Okay. Does not in this case. So, here's the argument we've already made. Volume was this. Bunch of pictures, bunch of details. One of the critical details was when we got around to computing the cross-sectional area, we were able to make this argument right here, that this was the height, because we were looking at a graph, and this, wrong color. This represented what you might call a length, right? Height times length gives you area, and two things worthy of noting. I know what that is. I have previous familiarity with this concept of area. That's a thing. And because I have a previous familiarity with that thing, I know how it behaves. And in particular, I like to say, accumulates. And let me come back over here to the picture and be explicit about what I mean by accumulates. When you're looking at this area right here, oh gosh, why won't it behave? Okay, close enough. The whole area is literally the sum of a bunch of little slices of area. The whole is the sum of the parts, right? And you've heard me say that earlier. By the way, in some sense, all single variable integrals are just kind of explicit examples of ultimately making that argument the whole is the sum of the parts. Right, so again, I know that that's true because I'm looking at the picture of it and I can see the area does in fact have this feature, and yes it is. I can imagine a bunch of slices, and that's just how area works, and I can argue that because I understand, because I've previously understood this idea of area. Okay, now let's try to, let's try to make the same argument now, looking at this mass of a sheet situation here. So again, it's tempting to just want to write down something like that. Right? Well, I mean, the volume under the graph worked out like this. Seems like mass ought to work out like that. It seems like it ought to work. Well, let's try to make sense out of it. Okay, and very importantly, let's try to make sense out of the argument. How would we argue that this is true? I'm not asking if this is true. I'm asking, does our argument supporting that this is true, does our argument make sense? And okay, here's our very first thing we have to make sense out of. There's this thing. This is mass per unit area, because mass is distributed over area, because it is literally a two-dimensional rectangular sheet. So fine, mass per unit area, which we are then multiplying by length. And now I have to ask, what in the world is that? Mass per unit area times length. Well, they don't cancel. Right? I can't say this is mass. It is not mass. Now, you might get real clever and think to yourself, well, area is length times width, and the lengths can't. Maybe I could view this as, could I view this as mass per unit width? Well, maybe. Then the question comes up, how well do you understand this new thing called mass per unit width? When, in fact, the mass is not distributed across width, the mass is distributed across areas. So mass per unit width, what is it? And does that have this critical feature? Does it accumulate? And if you have an answer to that question, are you sure? What are you basing that answer on? And I'll tell you what I think. I think that we're barking up the wrong tree, right? Best case scenario. Best case scenario, we make a bunch of arguments and develop a bunch of intuition and persuade ourselves that yes, we do understand what mass per unit width is and that it does in fact accumulate, and then we can make an argument about this one application. And then guess what? When we have to subsequently make sense out of an argument where we compute, I don't know, population or work or probability or any of a number, bazillion other possible examples, we've got to do the whole thing again. I would have to make sense out of what is work per unit area times length? Oh God, work per unit width. What does that mean? And you got to develop all that intuition all over again. This is a bad idea. It doesn't just work. No pun intended. This is a slog with every single application we've got to do. So I'm going to say we should abandon this. This is not a good approach. And here's a much better approach. It's going to be something called double integrals, which is importantly different from iterated integrals. And to motivate it, I've got to go back to single variable calculus for just a quick minute. Let me remind you, I hope you remember this, single variable integrals are Riemann sums, or if you prefer, limits of Riemann sums. Now this is commonly misunderstood. Very commonly misunderstood. When I first took single variable calculus, I just straight up misunderstood history. I thought this was the outdated formula that got obviated by the fundamental theorem of calculus when Newton developed calculus. Nope. Riemann sums came around about 150 years after calculus was developed. Okay, so that's not what this is. And then I thought, okay, well, yeah, but this is some formal, stuffy ivory tower nonsense that, mathematicians like to get all rigorous and finicky and persnickety about things. And come on, let's be honest. All you need to understand about integrals is that they give you area under a curve, and everything else is formal nonsense. This is really wrong. This is really wrong. If you are interested in applications, if you're an engineer, for example, as I think many of you are, you desperately need Riemann sums, if only as an underlying concept. But every time you compute something with integrals, you are using Riemann sums. All of this business right here is, you just can't get around it. You really need this. And let me show you why. This is what I like to call a little strategic diagram, diagram of connections between various objects of interest. And yes, it is true that area can be computed by an integral, which you can compute with the fundamental theorem. Yeah, fine. And then yes, it is true that you can take an application question, something about the physical world, let's say mass of a rod or whatever, and you can compute that too. And let me tell you how poor nonsensical arguments sometimes go. Sometimes the very first thing that they'll say when they want to compute mass is they'll say, okay, well, we're going to compute mass. Well, mass is area under a curve, right? Why? They're completely different things. Mass is all physical and stuff, right? Area is not. Mass and area are really different things. Didn't we say we were computing the mass of a rod? The rod is intrinsically we're treating it as if it's intrinsically a one-dimensional thing. What area? Right? This does not make sense. And again, I remind you, our goal here is not to get answers by some hocus pocus that we don't understand, right? Our goal here is to make reasonable arguments. I'm not going to get all formal about rigor and stuff, right? But we need to have some sequence of logical thinking that gets us to our answer, not just the answer. Again, you've heard me say this a million times. This is, of course, about reasoning, not answers. So this does not hold water. Now, a lot of people like this idea, even if it doesn't hold water. And so they say, look, the reason that this is true is because, and then they make some argument about how, well, if you take the mass in question, and just imagine looking at little pieces, they basically flirt with, they don't ever quite come out and get all precise about admitting that they're making an argument that is ultimately a Riemann sum. But the better the argument is justifying this nonsense, the more, in fact, it is just literally arguing about a Riemann sum. Okay? So, ultimately, then, these arguments go like this. They say mass, we're initially going to describe that as a Riemann sum, which I feel comfortable, right? It's my little security blanket to think of that as being an area, which I will then call an integral, which I will then compute with the fundamental theorem of calculus. And that's what those arguments ultimately end up being. And then the observation, the easy, natural observation to make is that, well, look, once you've connected that mass, and by the way, any other application that you might be interested in, computing with a single variable integral, the very first thing you're going to have to do, honestly, to make an argument that holds water is break it up as a Riemann sum. At which point it's, I think, not only valid, but I think important to recognize that, okay, well then I don't need to make any arguments about area. This is one of the reasons why I think it makes loads of sense to define integrals as Riemann sums, because then I don't need to go around for no particular reason and talk about area. Why would I talk about area? I don't need area. I can compute integrals with the fundamental theorem of calculus, and area is not relevant to this argument at all. Everybody see that? Okay. Now I know that, again, Calc 1 classes, and I'm not even judging. Right? A lot of people who take Calc 1 don't need to take multivariable calculus, and what I'm trying to prepare y'all for is stuff that a lot of Calc 1 students never need to encounter, and so maybe it's okay that Calc 1 classes do it that way. But it's a problem for our purposes, okay? And so I wanted to make sure everybody understands why it's important that integrals are Riemann sums. This is not mathematician formal nonsense. Stuffed shirt kind of, fussiness. No, this Riemann sum construction is the only way that we can make meaningful arguments to answer application questions. So if you're an engineer and you're anti-rigor, anti-formality, anti-fussiness, good. You desperately need Riemann sums. And I just want to make sure we're all clear on why we need that. Okay. All right. Okay. Let's see here. So what we're going to do, we'll start here just a little bit. We're going to try to generalize this now to a higher dimensional setting. And just to remind you, here's how we break up a domain in single variable calculus, right? You break it up for interval from A to B, and you have these formulas for delta x and x sub I, and then we write down this expression for the Riemann sum because, well, whether you're computing area under a graph or whether you're computing the amount of work that it takes to blah, 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 or whatever your application is, all of those examples, all of those applications, you'll be looking at little pieces of the domain that'll have a delta x that will be multiplied by something. Mass per unit length, work per unit length, area per unit length, aka height, if you're thinking about area under a graph. So some notion of size that gets multiplied by some notion of density, the products of which get added up take a limit to make round-off errors go away. This is everything we do with single variable calculus. And next time, we will talk about how to generalize this process to a two-dimensional setting. Okay, see y'all later. Have a good one. Let's see. Oh, I'm already out of